Okay, this is problem 3.1. We have a weight of 50 newtons. Not mass, this is a weight. Easy mistake to make. From a spring where K equals 4,000 newtons per meter. Harmonic force of amplitude 60 N. And frequency is 6 Hertz. Alright, so we imagine that this is a hanging mass, so it looks something like this. There's our K. There's our weight. Some harmonic force assumed to be F naught sine omega t. And X is going to be positive in the downward direction because that's a typical convention with a hanging weight. Alright, A, we're going to find the extension of the spring due to suspended weight. This is a static deflection. So our static deflection is equal to mg over k. This is pretty straightforward. This is the basically we could say that with static deflection the forces are zero, so mg has to be equal to k times the static deflection. So then we just solve for the static deflection. Dropped it again. Sorry, just dropped my microphone again. So this is a static deflection, piece of cake. The answer comes out to be 0.0125 meters. So 12.5 millimeters downward. Alright, so B. Okay, the static displacement of the spring due to max applied force. Alright, this is assuming basically that the force is at its largest value. What is the deflection that it's going to cause? Alright, so this is F naught divided by K because kind of the definition of a spring is that the force is the force on the spring is over the force created by the spring is equal to K times the deflection. And we want to find a case where the forces will be balanced because deflection is at a maximum. Everything's pretty much at a maximum when it's changing direction. So at a time when it's changing direction, net forces will be equal to 0. So we can conclude that the reactive force is equal to the force caused by displacement at that time. Alright, again, pretty easy. Answer comes out to be, come on. My computer's freezing up. Okay, that's not what you're supposed to do. There we go. Come on. My tablet is having issues. There's no way I'm going to be able to do this. Hold on. Let's see if I can get this fixed. Okay, that was very, very odd. So this number comes out to be 0.015 meters. So this is 15 millimeters. We can conclude that the harmonic force is stronger than gravity in this case. Okay. C. The amplitude of forced motion of weight. Forced response. I honestly don't understand what he's asking for half the time, and that creates a whole lot of problems because I don't know where to go. Alright, so for this, it's saying that the Let me just go ahead and write this out, and maybe as I'm writing it out it will make sense. Okay, this clearly looks familiar. This is generally amplitude. Okay, so this is the amplitude of the force. Okay, I see what this is the I guess this is the position at any given time. Yeah, this is the function of x of t. This is the amplitude. The amplitude of deflection, I suppose. I'm not really understanding how this is not the same thing as that. But well. Okay, so when it's asking for the... Okay. Anyways, there's no damping, so my zetas just get to look more and more like rho's all the time. Zeta equals 0. So then the amplitude is, I always get 5's and f's confused. I don't really know why. F naught over k over the absolute value of 1 minus omega over omega n squared. And this is the simplified version due to zeta being equal to 0. We already know, well, we can already calculate omega n. The square root of k over m is 28.014 radians per second. Alright, now the frequency is given to us, but not the angular frequency. So it's 2 pi f as 2 pi times 6 hertz is 37.699 radians per second. Alright, so we've got our omega n. We can plug those back into our amplitude, and we'll get 0.0185 meters. Okay, so this is the amplitude of the forced motion. And I don't know why it does not correspond to this. Maybe it's because G is also a restoring force? No, it's not. It's not really. I don't know. Oh. Because the spring and the applied force could be interacting in such a way to create a deflection bigger than the two of them combined. That has to do with resonance. We are actually above resonance here. So, anyway. So that's your answer for this problem. Things to make note of. This is probably a dead giveaway. You just want to make sure you know it in these particular applications. The wording is kind of weird. Static displacement of spring due to max applied force. This is applied force, whereas this here is just gravity. Alright, and kind of remember this. This is the function of x at any particular time is the amplitude times sine times the frequency. This is our angular frequency.